Hello everyone, I am Chengqian and I will discuss using learning-based techniques for inverse scattering. Scattering materials are everywhere. A cup of milk, an engagement ring, a forky highway, or our own skin are all made of scattering materials. Because of the ubiquity of these materials, applications related to scattering are critical in many different fields. For example, in medicine, recovering tissue scattering parameters is used to diagnose the presence of tumors. In AR/VR applications, knowing the scattering properties of translucent materials is necessary to reproduce them in virtual scenes. In industrial manufacturing, it is necessary to inspect the scattering behavior of fabricated objects in order to detect any defects. Importantly, in all of the above applications, there is increasing demand for computational techniques that can infer scattering properties in real time with minimum calibration and at the same time without sacrificing physical accuracy. All of these are instances of a problem we call inverse scattering. Given an image of a translucent object and potentially knowledge about the scene, we are looking to use computation to predict the optical properties of the underlying scattering material. We take first steps towards making inverse scattering possible in real time and in completely uncalibrated settings where no scene information is available. To this end, we first introduce a new inference pipeline, the inverse transport network, that combines neural networks with physics-based rendering to achieve both computational efficiency and physical accuracy at test time. We then show how to modify this pipeline so that it can tackle a class of ambiguities called similarity relations that confound inverse scattering. Finally, we create a new dataset of 30,000 rendered images of translucent materials and use it to evaluate our inverse scattering pipeline. Let's start with the first part. For this, it is worth taking a quick look at the physics of subsurface scattering. As a light source illuminates a translucent object, photons travel at its interior before being measured by a camera. This process can be modeled using radiative transfer, which describes materials using a set of optical parameters. Despite the complexity of subsurface scattering, we have powerful forward scattering algorithms that can simulate not only the physically accurate images of translucent objects, but also image derivatives with respect to scattering parameters. As we mentioned earlier, we are interested in the inverse process of mapping images to material properties. We can broadly categorize such inverse scattering techniques into two large groups. The first is analysis by synthesis techniques, which optimize for material parameters that, when combined with forward scattering simulation, produce images that match the inputs. Because we rely on forward scattering simulation, analysis by synthesis techniques are typically very accurate, but also very computationally expensive and require additional knowledge of the scene, geometry, and lighting. The second group of techniques approximates the inverse scattering function using a neural network. Such a network can be trained using a supervised loss, comparing network outputs to ground truth parameters. These techniques are computationally efficient, requiring just a forward network pass at test time, and can operate without any additional scene knowledge. However, they are not physics aware, as they do not account for the forward scattering model. To combine the advantages of these two types of inverse scattering techniques, we propose a physics-aware learning pipeline that we call inverse transport network. It works by concatenating a neural network and a forward scattering simulator. During training, the network outputs material parameters which are used by the simulator to synthesize a new image. By requiring that this matches the input image, we force the neural network to act as the inverse of the forward scattering function. Our training loss has two terms. First, A supervised loss compares the network output to ground truth material parameters. Second, an unsupervised loss compares input and reconstructed images. In order to train the network, we need to backpropagate from the reconstructed image back to the network weights, which requires two sets of derivatives. First, the derivative of predicted parameters with respect to network weights, which is easily obtained using auto-differentiation. Second, the derivatives of the forward scattering process with respect to predicted parameters, which we compute by implementing our own volumetric monocolo differentiable renderer. At test time, the inference requires only a forward pass through the network. Thus, inverse transport networks can predict material parameters efficiently without any geometry and lighting information, and in a physical-aware way thanks to the integration of forward scattering in training process. As we show in our experiments, inverse transport networks already significantly improve inverse scattering performance. Next, we discuss a couple of design choices that improve performance even further by enabling the networks to handle similarity relations in scattering. These similarity relations characterize ambiguities in the form of different material parameters that produce very similar appearance. We discuss two ways of overcoming these ambiguities. First, we take advantages of the fact that similarity relations are strongly dependent on lighting and geometry. Let's look at these two cubes made of materials satisfying similarity relations. They both look the same at thick and smooth surface parts, but they have different appearance near thin geometry features, such as edges. Therefore, we can mitigate similarity relations by training our network to emphasize appearance near geometric edges. To achieve this, we first use a simple algorithm to generate a per pixel weight map for any given input. Each pixel is weighted based on its distance from the nearest detected edge, as shown in these examples. Then, we use these per pixel weight maps to augment the appearance training loss so that it emphasizes the appearance difference near geometric edges. Our second approach for dealing with similarity relations is to reparameterize the material parameter space. We adopt a nonlinear transformation developed in the scattering literature so that materials with similarity appearance are closer in the transformed parameter space than in the standard parameter space of the radiative transfer. We now move on to some experiments evaluating our inverse scattering techniques. We evaluate three different networks. First, a baseline that is trained using only the supervised parameter loss. Second, our inverse transport network incorporating the unsupervised appearance loss. And third, our inverse transport network modified for similarity relations. All three networks use the same architecture inspired from the previous works. For our experiments, we created a new dataset of 30,000 HDR images using physically accurate monocolor rendering. We split our dataset into training and testing sets with no overlapping lighting and geometry conditions. We evaluate our networks in two settings. The first is an uncalibrated setting, where only a single image of the unknown object is available. We use each network to predict material parameters and evaluate the predictions using three metrics: a parameter loss comparing it to the ground truth parameters, an appearance loss comparing the reconstructed and input images, and an appearance loss between renderings for novel things. Here are some examples. We compare input images to images reconstructed from network predictions. From the error maps, we see that both of our networks reproduce the input appearance much more closely than the baseline, with the similarity networks producing the best matches. the network improves all our error metrics by 40 to 50% compared to baseline. We additionally evaluate our networks on photographs of two real objects. Each network uses only the photograph as input to predict material parameters, which we use to render approximate versions of the real thing for evaluation. The predicted parameters successfully approximate the appearance of the two objects, including important features such as intensity gradient near edges. We also evaluate our networks in a calibrated setting where, in addition to an input image, we have full knowledge of the scene geometry and lighting. In this case, we can use analysis by synthesis together with gradient descent and our volumetric differentiable renderer to accurately infer the material parameters. We also use the prediction of our networks for initialization in order to significantly accelerate convergence and help avoid local minimum. We show an example for one image in our dataset. The initial predictions from both our two inverse transport networks produce images that match the ground truth appearance much more closely than the baseline. We then use these predictions to initialize gradient descent. We observe that at the same number of gradient descent iterations, analysis by synthesis initialized with our best network reproduce appearance better than when initialized with the baseline. Across our dataset, we have narrow improvement of 50% or a 2x convergence acceleration. To conclude, we have taken first steps towards enabling computationally efficient, uncalibrated inverse scattering through a learning architecture that incorporates forward scattering physics and accounts for similarity relations. Thank you for your attention, and please visit our website for all our data and code.